Good morning. Let's continue with multiple reactors. Let us have a recap of what we did in the last video. What we did was, see, if we were using equal sized CSTRs and first order reaction, we did a few calculations and we found that see tau dash was equal to 3.88 for 6 tanks, and tau dash was also equal to 3 for n tanks. So what do we actually understand from this is, if we are using 3 meter cube CSTR, if we are using one tank of 3 meter cube then if we use 6 tanks, it is enough. We need not go with more than 6 tanks, because though we use conversion was fixed, that is 95%, 0.95, x is equal to 0.95 was fixed. Okay, so for this conversion we found we tried to find the volume of reactors. Then we found something. When we are using 6 tanks of 3.88 meter cube, 95% conversion. If I increase the number of tubes also of the same volume, also 0.95% only conversion. So why do we need to go for many number of tanks? That is one conclusion. And next thing is, I want to explain Damkohler number. Damkohler number. He's a German. What is this Damkohler number, and what information does this give? Okay, so this Damkohler number, it is written as K. Did I introduce that? Okay, I have not introduced that, right? Okay, Damkohler number, it is denoted by dA. And it is written as K tau Ca0 to the power of n-1 for any order reactions. So this Damkohler number, what it helps is, see, this helps us to find the extent of conversion. I mean, this speaks about the extent of conversion. So for a given reactor, the rate constant is known. Tau volume of the reactor by volumetric flow rate will be known for a given reactor. And Ca0, the initial concentration, which is fixed. Okay, and order also is known to me. So first thing, we will find Damkohler number. If I find Damkohler number dA, if the Damkohler number, by this formula I can find Damkohler number. If dA is high, then conversion is high. Okay, so how does this help me? This helps me to select the reactors as well. So yeah, this is about the Damkohler number, and this Damkohler number, this will be K tau. If this n is equal to 0, it will be K tau by Ca0. This is for zero order reactions. If n is equal to 1, Damkohler number is K tau for first order reaction. If n is equal to 2, Damkohler dA will be K tau Ca0 for second order reaction. Okay, so these are the few. This is the significance of the Damkohler number. If higher the value of Damkohler number, higher is the conversion. So higher is the conversion means what type of reactors are to be selected. So for higher conversions, usually we go with PFR, and higher orders also we go with PFR. Yeah. Let me have one more just a recap of what we have done when we were comparing the volume of PFR and MFR. See, what did we do there? What did we conclude there? See, for n greater than 1, volume of PFR will be better. PFR is better because volume required for a PFR will be lesser compared to if I'm using a CSTR. Okay, then orders less than one, MFR will be better. So for lesser conversion, if the conversion is around 30%, 40%, then it is better to use CSTR. Okay. And if and n is equal to 0, we saw that volume of MFR and PFR both are same. So whichever reactor we use, whichever can be used, PFR or CSTR, both can be used. Anyone can be used. Okay. Then what did we say? N is equal to 1. N is equal to 1 also we proved PFR is more efficient. PFR is more efficient. Yeah. So this was what we had done in the last class. Just a recap of what we did in the last class. Why I discussed that is later I'll be going for connecting these reactors. Okay, so that's why I have given a recap. Let me rub this. So let us work out on connecting these reactors. Okay, so there are three reactors given to me. One is PFR, large CSTR, and small CSTR. This PFR, large CSTR, small CSTRs. Okay, so these are some of these reactors are available now. Okay, so now how are these reactors to be connected to minimize the volume? So when we are speaking about multiple reactors, no, we are speaking about minimizing the volume. Next unit, I'll be speaking about multiple reactions. There, we will speak about maximizing the yield. Hope you're getting the difference between these two. Minimize the volume. So smaller volume reactors trying to get maximum product. Multiple reactions, maximizing the yield. Okay. So now these three reactors are available. How these are to be connected. So here we will be discussing two cases. That is one n greater than 1 and n less than 1. So let me go with n greater than 1. Obviously, we have concluded for higher order reactions, PFR is better. So first, which one I should connect? I should connect a PFR first. Later, I'll show this in graph also, how these things are better. Okay, next. Next is what? A small CSTR. A small CSTR should be connected. Small CSTR. Next is a large CSTR. Large CSTR. Okay. So now if I'm trying to plot -1 by RA versus X, and this also depends on the curve what we get. Okay. The nature of the reaction what we get. Okay. So if I'm connecting PFR first, okay. So if I'm connecting PFR first, this is the area under the curve. This will give me V1. Let me call this as V1, V2, V3. Okay. So this gives me V1 by Fa0. Okay. And next is second one. Second CSTR if I connect now. Second CSTR if I connect now. So how do I find? So this will be. I should go with X1. So here it will be X1, X1, X2, X3. Okay. So what should I do with X2 only? I should go horizontal. From X2 only I should go like this. Okay. So this will be the V1. This will be the V2 and V2. Okay. Next, if I go with a large CSTR, here also X3. X3 is here. From X3 only I should go horizontal. Till when? Till X1. Okay, so this will be the value. Okay. So this is for small CSTR. This is for a bigger CSTR. And this is for a PFR. This is for a PFR. So this is how they are to be connected. This is how they are to be connected. Okay. So if I'm trying to okay. So this is about when n is equal to, n greater than 1. Next is n less than 1. If n is less than 1, if n is less than 1, what should be the order? Order is the reverse of this. Large CSTR is to be connected first. Large CSTR. Okay. Then small CSTR. Then a PFI. Okay. So if I'm trying to plot this again, minus 1 by RA versus X, and if the nature is in the same way, okay. Oh, fine. If n less than 1, no, the nature will not be in this way. Nature will be the reverse. It will be in this way. If n is less than 1, nature is in this way. Okay. So, x1, right? x1, let me mark them. x2 and x3. So x1, from x1 vertical and then go horizontal. Okay. Then from x2 again vertical, horizontal, and this will be the area under the curve. Okay. So for CSTRs, large CSTR, it's the reverse now, and a smaller CSTR, and then a PFI, area under the curve. Did you observe how I did that? See, for PFR it is area under the curve. For CSTR, it's the rectangle. Okay, so we can make a note of this. Note of that. Okay. Next thing is, I would like to go with graphical method for MFRs in series. This is very nice, very fun to learn this. Okay. So graphical method for CSTRs in series. Okay, graphical method. For CSTRs in series. Okay. So how do I proceed is, so first thing is C0 is known to us. C0 will be given. I mean, that's a given concentration. Okay. And let me draw a schematic diagram for, let me take 2 CSTRs here. It goes on. Okay, yeah. And first case, I go with V1 equal to V2. Okay. Usually in industries, when we are connecting multiple CSTRs in series, no, we try to have same sized reactors. Okay. But very rare in some cases we may have to use different size reactors. So when we may have to use different size reactors, I'll go next. So let me just complete the graphical method for the reactors which are equal in size. So let me graphical method. So let me have a plot of minus 1 by RA versus CA, and the concentration curve. What I'm taking is, this is a concentration curve. Okay, so concentration curve is higher. This will be CA not here. Okay, CA not. Anyway, I don't need that line. Let me rub it because that will be confusing. First, what I'll do, what we will do here. First, mark CA naught. Okay. Then we know the performance equation. Tau by CA naught equal to XA by RA. No? If I'm writing that in terms of concentration, if I'm writing that in terms of concentration, it will be tau A1 is equal to C0 minus C1 by minus RA. Minus RA. Okay. Or now I can write this as minus RA1 by CA0 minus CA1. Okay, CA1. CA or C1 or CA0 or CA0 all the same. Will be equal to minus 1 by tau 1. Okay. Similarly, minus RA2 by CA1 minus CA2 will be equal to minus 1 by tau 2. So now from CA0, what I do from CA0, I try to get this slope minus 1. So this is the slope. Okay, so I try to mark the slope from CA0, and it should be a straight line. This is minus 1 by tau 1. So now where does it look? It's not looking straight. Let me come back. Okay, so this is minus 1 by tau 1. Okay, minus 1 by tau 1. And this will be RA1 and CA1. You will write X and Y. No, so this will be CA1. Okay, so first the procedure is first locate CA1. Then find the slope, and then mark that slope so that it intersects the rate concentration curves. And from there you drop a vertical and try to find CA1 on the x-axis. Okay. For a CSTR, no, on the rate concentration curve, you can get R1 and C1. R1, C1 can be shown on the rate concentration curve. Okay. So for the next reactor, let us repeat the same procedure. So if the volumes of CSTRs are same, then the next slope what I draw should be parallel to minus 1 by tau 1. It should be parallel if they are equal, if they are of equal size. Okay. So it's parallel. Yeah. Now it's a bit parallel. Okay. So this is minus 1 by tau. And from here, if I drop a vertical, this will be CA2. Okay. So like this I can continue, and from here again I'll go parallel to this. I'll go parallel to this, and this will be CA3. So here I have used, suppose my value, my final concentration is only this. My final concentration is CA3. It's good. By connecting 3 CSTRs, I can obtain CA3. That is the meaning. And CA3, and you can see all are equal all are of equal volume. All the reactors what I'm using here are of equal volume. Okay. So this is one method. This is one method of finding the number of CSTRs required. Okay. So from my experiments, I will know CA0 and CAF. Okay. So suppose in this case, my CAF is this value. My CAF is CA3. It is very simple. If by connecting 3 equal sized reactors, I can arrive at this. So from this I can make out okay, three reactors of certain volume. I can find the volume. 3 reactors of certain volume are enough to give me CA3. Okay. So good. We have finished this. The next thing is, when do we go for different sized reactors? Okay. This is very interesting. When we have to go for different sized reactors. See what happens now sometimes when we are plotting minus RA versus CA, the same plot I'll take, and the same nature of the curve I'll take. Okay. So here my CA naught and CAF, suppose they are fixed. CA naught and CAF are fixed. Okay. So now and I have a reactor. I have a reactor of certain volume. So for that, first I'll find the conversion and I'll try to plot that. Okay. And I'll repeat this. I'll repeat what I have done for the previous one. Okay. And yeah, this here I go with CA1. And if I'm plotting parallel, parallel to this, see, so many lines are seen. Plot a line parallel to minus 1 by tau 1. 1 by tau 1. Okay. So, and I'll get CA2 here. CA2, again the same I'll repeat for this is minus 1 by tau 3 and see if I'm using equal sized CSTRs, here I'm using equal sized CSTRs. Okay, I'm getting this. Okay, and yeah. So you can observe here what CA2, CA3, CA4, CA5. Okay, but CAF is still here. CAF is still here. You can observe the CAF. Let me denote that. If I'm what did I do? I tried to connect equal size PFRs. Here CA0 and CAF are fixed from the experiment. CA0 is given and final conversion is expected. Okay, this much conversion is expected. So for that, I'm trying to find out how many are to be connected of a given volume. Okay, so when I'm trying to do that, I found if I'm connecting equal size CSTRs, the final conversion remains somewhere here, but requirement is here. CAF is here. So what should I do for this? So in these cases, they'll go for different size reactors. Of course, this is just for general knowledge. This is just for information to know what really happens in the industries. Of course, this need not be studied for your. This is not there for your. This is not there in the textbook also. I'm just explaining you so that you have thorough knowledge on what really happens in the industries. Got it? So the CAF compensate for this. To compensate for this, the volumes of other reactors will be changed. Either that can be done or the volumetric flow rate can be altered. So tau is V by V naught. So I can use different sized CSTRs and I can alter the volumetric flow rate of the CSTRs. That is how. Okay. So I said this is very fun learning. It's very interesting to learn. Okay, I have some reactions going on. So if I want to connect CSTR, if I want to use CSTRs, how do I connect them? If I have equal sized, how do I connect them? If I have equal sized and if I have to match the conversion, how do I convert them? How do I connect them? All this is about multiple reactors. Very interesting topic, subject, chapter. Next is autocatalytic reaction. Autocatalytic reactions, I have just told you what is an autocatalytic reaction. So for autocatalytic reactions, MFR is better or CSTR is better? Which is better? Keep thinking. Autocatalytic means what? One of the product form is required for the reaction to proceed at a faster rate. I'll write an autocatalytic reaction. A plus R gives R plus R. Okay. So here, initially what happens if I'm conducting this in a batch reactor, if I'm conducting this in a batch reactor, initially what happens, the concentration of A is very high and the conversion will be slow because this requires R to proceed faster. But I don't have R initially. But after some time, after certain period of time, R is formed. R is formed in the batch reactor only. I'm speaking about batch reactor now. Okay? So R is formed in the batch reactor. Once there is R in the batch reactor, the reaction starts to proceed faster. Okay? And till when it proceeds, till all the A is exhausted. Till all the A is exhausted. Okay? So the nature, if you are plotting, initially it is very slow, and somewhere it reaches and suddenly it drops down. Okay, it drops down. So yeah, and if I am trying to show that minus 1 by RA versus, we have taken minus 1 by RA. Okay, so CA naught is fixed, right? CA naught is fixed. So initially the reaction proceeds like this and slows down. I said no till this is a maximum. Okay, so maximum R this here, when I plot this one, there is no R in the field. No R in the field. Okay, now what happens, I try to take little R already, before starting the reaction. So before starting the reaction, if there is some R initially present, then the reaction will be somewhere like this. So this is with R initially present. Okay, some R in the feed, with R in feed. Fine. Next, if I show this in terms of conversion, minus 1 by RA versus XA, this is the progress of reaction. Direction is in this way. Progress of reaction. If I'm trying to plot minus 1 by RA versus XA, the progress is in this way. Progress of reaction. Okay. So, and this is the point of maximum rate. Point of maximum rate. Okay. Yeah. So this is actually rate versus concentration curve for nth order reaction. Now let us discuss on how about using a plug flow or a mixed flow for a autocatalytic reaction. Okay? So when I say autocatalytic reaction and a PFR, so just think about this. What's a PFR? In PFR, there is no mixing. The reactant enters and it leaves. So, but for an autocatalytic reaction, there should be some product in the feed, right? There should be some product in the feed. Okay. So, can I use this PFRs directly? Yeah. Keep thinking. Okay. Let me come to that point. Keep thinking about that. Okay, so now this is size comparison of CSTR and PFR for autocatalytic reactions. So minus 1 by RA versus what I've taken XA, and the nature may be any type. Okay, minus 1 by RA, and this is a bit steeper curve. And okay, so if the conversion is less, suppose the conversion is here only. If the conversion is lesser, let me show XAF here. If the conversion is less, see which will be better from XAF only. If I'm trying to find the volume of MFR, volume of MFR from XAF, go straight up, then take horizontal till the curve, then take horizontal path, and this gives me the area. If it is PFR, this will be the area. Sorry, MFR. If it is MFR, this will be the area. Okay. Now, if for same XAF, if I am using a PFR, for a PFR it is integral of dxa by minus RA, right? So it should be this total area under this curve. So I'll show MFR, PFR in green lines. So this is volume of PFR. This is when conversion is low. See here, XAF is very here only. Low conversion. I had also told this in the beginning of today's class. So low conversion, which is better? Here, volume of MFR required is lesser compared to the volume of PFR. So I say MFR is better here. MFR is better. MFR is better. Okay. And at certain conversion, at certain conversion, at some if the nature is in this way and somewhere getting the nature in this way. So if you are trying to find this will be the volume of CSTR, volume of MFR, and for a PFR I should show from here now. I should bring a different direction. So if you calculate, for PFR it is all this rectangle. Okay. So if you calculate here, almost volume of MFR is equal to volume of PFR if the curve is, if the nature is in this way. Okay. Next, let us go with higher conversion. Suppose higher conversion means almost here. XAF. Okay. So if this is XAF, what will be the area? This is the area for CSTR. It is almost a big rectangle like this. So I have to take this entire area. Okay. So that will be PFR. Red. This will be the volume of MFR. This is the volume of MFR. And if I am trying to find PFR, it is area and it is area under this curve only. Under this curve. So which is lesser? Volume of PFR is lesser. This is volume of PFR. So volume of PFR is lesser means PFR is better here. PFR is better here. Okay. Then, I had given you something to think, right? See, if I'm using a PFR, this is a fresh feed. Okay. And this is the effluent or the product stream. Let me not write that as effluent, I'll write that as product. Okay. So for an autocatalytic reaction, it can proceed faster if there is some amount of product. So what should I do? For this PFR, I'll try to put a recycle stream. Of course, there is a derivation for recycle reactors, but that is not included in the syllabus. It's a very nice derivation and very nice concept. Recycle reactors are very interesting because they are very interesting reactors. But I'll just define one new term here and I'll leave at this stage. Okay. So if you want to improve the performance of the PFR for an autocatalytic reaction, if it's given a recycle, it will give better performance. Okay. Yeah. I said I'll define a new term, no? Recycle ratio. Okay. So this is volume of fluid This is volume of fluid returned as recycle divided by volume of fluid leaving the reactor. Okay, yeah, make a note of this. And one small thing, let me complete and conclude today's session. Yes, make a note of that. Okay, this is reactors of different types in series. Reactors of different types in series. Reactors of different size, different type. It is different type now. Type in series. Okay. So now if I have a CSTR first and then it is connected to a PFR, CSTR, and then this is again connected to a CSTR. Okay. So it is just a practice how we write the equations, how we find the conversions. Okay. So first one, this will be C1, C0, C2, C3. V0, V1, V2, V3. Okay. So for the first CSTR, if I write, it is V1 by F0. F0 or FA0 I've taken. Okay, I've taken that as F0 only. This F0, the F0 is same. Okay. V1 by F0 is equal to C1 minus C0 minus C1 by minus R1. Have I written in terms of, okay, in the notes I have written in terms of tau 1 by C0 is equal to x1 minus x0 by minus R1. Okay, so if I'm writing this, then V by F0 is equal to 1 by, okay, C0. Of course, I don't need this form. I'll just go with in terms of T. So tau 1 by C0 is equal to x1 minus x0 by minus R1. Okay. So the next one is V2 by F0 is equal to 0 to dx by minus R, and this is x1 to x2. Okay. And for this it is V3 by tau 1 by C0 is equal to V by F0. Okay. V3 by F0 will be equal to x3 minus x1 by minus R. Okay. Now if I plot this, and the nature is 1 minus 1 by R versus x, nature obtained is using this way, then yeah, it is CSTR first. So CSTR first. So this will be the CSTR, volume of CSTR required. Okay, and then it is PFR till here, suppose it is PFR. Okay, and then it is again CSTR. CSTR if I'm finding, I should from XF, X final, I should go here. It is 3 right here. 3. It is x2. It is x1. So this will be the area for CSTR, last CSTR. Okay, so this is how we get. Okay, and now if I'm going in the other way, like I'll take two PFRs here and a CSTR here. Let us study that also. Two PFRs and then a CSTR. So now you have overall ideas when to use PFR, when to use CSTR. Main aim here is minimizing the volume. Note that, minimizing the volume. I kept on telling minimizing the volume. So V0, C0, F0, V0, C1, F0, V0, C2, F0, V3, C3, F0. Okay. Oh, F changes. Then F is equal to C1 into V0 here. C1 into V0. Okay. But I'll try to maintain F0 common, a constant here. I'll try to maintain a constant. So for this, I can write as tau1 by C0 is equal to x0 to x1, 0 to x1, dx by minus r1. And for this, it is tau2 by C1 is equal to x2 minus x1 by minus r1, and this is tau3 by C3 is equal to x3 minus x1 by minus r1. Written correctly. V by f naught is equal to tau by C naught, or this is also equal to V1 by f naught, V2 by f naught. This is V3 by f naught. Okay, and if I'm plotting minus 1 by RA versus CA, and the nature is in this way. This is the nature. This is the nature. Okay. So what do? We have to start with PFR. So for the PFR, it is area under the curve. Okay. And for CSTR, it is from x2. I should go straight up till the curve, and so this will be CSTR. This is just for practice, for you to understand and practice. Okay. Next is again PFR till x3. So this is area under the curve only. For x3, it is area under the curve. Okay, so this is PFR, which is area under the curve. And for CSTR, this. So, yes, now you have a thorough knowledge. So, depending on the order, which is the best reactor, and depending on the nature of the minus RA versus minus 1 by RA versus concentration curve obtained. So which reactor to be selected first? And when we will go for selecting different size reactors. So you have a thorough knowledge of all these things now. So let us proceed with the sums, with the problems. Okay. Yes. Thank you.